Meng, first of all, I just wanted to thank you so much for taking time out of your very busy schedule to talk with me today. I am super excited to do an employee spotlight with you based on your current work that you do for SSAI. My first question I wanted to ask you was, what drew you to SSAI, and how does the company's mission resonate with you personally?
Okay, thank you, Jason. It's truly my honor to be in the spotlight. So I think I have a kind of unconventional path which lead me to SSI, because when I'm in grad school, actually my research work to study cuttlefish cephalopods. We try to understand how they can camouflage. Sometimes they can put on their like visible, fantastic patterns to be invisible to their predators, but also turn on some kind of polarized pattern so they can still communicate their friends. So that means they really know a lot of optics. And my work is to understand how to model them. So we learn a lot of stuff like the physics, how the light scatter in their cells, and learn those from the atmospheric physics, from optics people who study oceans. And eventually, those studies actually prepare me to do the work which what I'm doing right now for SSAI. Because right now I support NASA's space mission, we use exactly the same physics, how to study light scatters for the aerosol in the air, some particles in the ocean, and the whole system to do remote sensing. Actually, they're all connected. So that's a kind of my approach or my way, which leads me to study a much bigger system. We used to study, the microphysics, only a couple of centimeters or even smaller. Now we study whole globe, 1,000 kilometers, right? I'm still really, really excited about it.
Wow, that's truly fantastic, Meng, and I really appreciate you bringing up your work with the PACE mission. And we have done spotlights in the past in regards to the PACE mission. So yourself, including all of our other scientists and employees who have been involved with this mission, have done such outstanding work. And just for our audience and viewers who are currently listening to this employee spotlight as well, please definitely check out our YouTube channel to see some of our recent videos that we did probably about a year and a half ago or so in relation to the PACE mission. So that way you can see further in terms of what all of our scientists, engineers, technicians have done, just like Meng here. So Meng, like I said, I really appreciate you highlighting more about that. And we've gotten some great data too, which is super exciting.
Exactly.
And Meng, I wanted to transition on to my next question that I wanted to ask you. You mentioned about your work on the PACE mission, and basically with your work on the PACE mission and the development of aerosol and ocean color retrieval algorithms like MAPOL and also FastMAPOL, those algorithms help us better understand the Earth's atmosphere and oceans. What are some of the real-world challenges these tools aim to solve, and how do you see your research at SSAI contributing to environmental monitoring and decision-making?
Yeah, that's another great question. And I'm really happy you already know that much about PACE and even already did some podcasts, for PACE. Mm-hmm. And so, we're still really excited about the PACE launch. It happened last year. So we have like a whole year data. We kind of play with it. We learn a lot about it. And also, in order to prepare, to process the data, we have been working on it for many years. That's related to the algorithm you mentioned. The MAPOL, we call it MAPOL, and there's also the fast version, we call it FastMAPOL. The FastMAPOL actually is the production version. And for MAPOL, we created like for research effort. We try to understand whether we have capability to do retrievals for the aerosol in the atmosphere, also do the ocean color studies. So after that, when we think about how we can apply it globally, and we develop the FastMAPOL, which is the production version. So back to the question. So I want to emphasize is, everything we are working here is all related or depend on the wonderful instrument which is built by our instrument teams. We have 3 instruments on PACE: OCI, HARP2, and SPEX1, and those instruments can measure a lot of really important stuff and also have really high accuracy. And not just that, they also measure things in different dimensions. They can do color measurement, different spectrum. They can look at things at different angles. And also we have the polarized measurement. and those measurements can provide us accurate information. And that's the instrument. So we have the wonderful instrument there to provide all those measurements. Another key thing is the physics model, so-called what we call it the rich transfer model. Basically, that model can do the modeling of the scattering of the single particles and then scale it up. So you can study how light scattered between particles. Like if we have clouds, we have molecules in the atmosphere, we have aerosols, how those interactions really happens and how they can eventually relate to the measurement. We have those theories there, we have model there. Also, we have our PACE team support sensitive people. We have colleagues in universities, and they have built really, really wonderful tool for us. But one disadvantage is they are slow because our requirement is so high. We want them to have really, really high accuracy. We want this model can generate so many things, all the interaction in atmosphere and ocean. The code is really complicated. We run really slow. So what my work or our team's work is really try to make sure we can run those really accurate retrieval code in production system. So we learn a lot of techniques from machine learning. During the last couple of years or decades, there's a lot of machine learning tools. So we actually educate ourselves. Actually, I'm supported by SSAI. I took some deep learning courses, and so we can using the tools and we can train a emulator, a machine learning emulator. We're using something called neural networks, and we can represent this kind of transfer model really, really accurately, and also really fast. We can, speed up maybe 3 hours, 4 hours of the magnitude, and that's really give us the advantage. We can apply those transfer model, physics model in production system. So that's where the FastMAPOL comes from. We basically replace the full physics transfer model by a neural network emulator, and then we can do a lot of testing. We can understand how they can retrieve aerosols, what the uncertainties. We can do a lot of testing. We can play with that. We can evolve from it. We can iterate, and then we have our current version already testing in our system. And the goal will be provide global aerosol and ocean color properties. For aerosol part, we can have aerosol size, shape, all kind of knowledge we have them, and we can understand how they can reflect light, how they can absorb light, how they can interact with the cloud, understand the basic energy budget of our Earth. And then we can also study air quality, a lot of things we rely on our knowledge of those global products. For ocean, the aerosol can also impact the ocean color. That's kind of also like a lot of work we are doing here in our lab, our ocean color lab. So we can produce really high quality ocean color data. So they all kind of connect to each other, and that's kind of our excitement come from. So we have all the data. Now we build the tools, and now we are open to a lot of opportunity of research.
Wow, I was going to say, Meng, that is truly fascinating and absolutely incredible. I appreciate you breaking down a little bit more in terms of the algorithms like MAPOL and FastMAPOL, and it's very fascinating. Those are a couple things that I didn't really know about, and you mentioned about the coding experience, and as a side note, I have very basic coding experience. I don't have quite as much as somebody like yourself and members on your team, but I definitely truly understand and relate to the fact that, it takes time, especially with all the data that's coming in. You definitely want to have very efficient ways in terms of, taking a look at that code, analyzing it, and as you mentioned, come up with the best data possible. And you and your team are clearly doing that, which is incredible. So we've seen some great snapshots on the PACE mission already, and we're looking forward to seeing so much more with that. So again, I really appreciate you helping to break that down even further. And then, Meng, my final question I wanted to ask you was, and this is a fun question, just as a side note, but the question is, if you could explain what you do on the PACE mission to a curious 10-year-old using only ocean or space metaphors, how exactly would you describe it?
Yeah, that's a great question. So, I actually have a 14-year-old kid in my house. He's always curious. I think probably I can, also try to convince him to do more science. So I think basic thing, or I try to think about like the big picture what we are doing here. We have satellite like 700 kilometers away, right, from our surface. The distance is always like from here, like DC to Boston. That's far. And then what we want to do is we want to study the microphysics. We want to study like, for the small particles, like tiny dust particles, they are really, really small, micrometers, like as small as our hair probably. Also, there are small particles, small hydrosols, phytoplankton in the ocean, also in the similar scale. So how we can study those microphysics, like small stuff, from something really, really far away with a macroscopic measurement. That's that's the thing we try to achieve. How we can study microphysics, micrometer stuff from something really, really far away. I think that's the question we try to answer. And the answer is always in physics, right? So we have a great measurement of, from all the wonderful instruments. Also, we have those physics. We understand how particles interact with each other. So we're not just seeing one of them, we are seeing a lot of them. And we understand how they interact with each other. So we can derive from those multiple scattering or the macroscopic measurement to derive single particle properties. And that's the goal. And we're also achieving it while producing really accurate microphysics properties for aerosols. As I mentioned before, we can study their size, their shape, and the reflecting index that's related to their composition. So we know what kind of particle is there. I think that's the kind of the secret message we try to decipher from the light. There's lots of messages there. And now we have the capability. And hopefully for 10 years old, maybe even older, when they think about what kind of physics or, the science is capable, hopefully they can be inspired and, doing something like that in the future.
Absolutely. Well, I think, Meng, that was very well said, and I really appreciate you highlighting how you would explain your work involved with a PACE mission to a curious 10-year-old. I loved how you related it to your child, and that's the whole point. We definitely want to get the next generation or any generation curious and, see how best it relates to them and, what's the purpose behind doing it. And like I said, you and your team are clearly doing that, and it's just super, super cool just to take a look at some microscopic items and see how far it is and measure it to something very, very far away. So again, I really appreciate you helping to break that down and explain that concept even further. And Meng, with that, I just wanted to thank you again so much for taking time out of your very busy schedule to talk with me today. You are truly a rock star who is really making an impact and a difference globally, and everybody around the world is going to continue to be fascinated by the great work that you and your team do. Please definitely keep us informed about continued insights and continued innovations that come from the PACE mission. Again, we've gotten some great data so far, and we cannot wait to highlight future things.
Great, thank you, Jason. Thank you for highlight our work, also our work for PACE. There's a lot of things we're expecting, so thank you so much.